In this video, I'm going to walk you through creating Netcdfs of our derived parameters or values, which are chlorophyll at depth for globally. So this is a follow-up of my other video of using boosted regression trees to make predictions. So here I'm using remote sensing reflectance as a predictor, and then I'm using a boosted regression tree to get a prediction. And now I want to serve those predictions as global Netcdfs. This walks you through the logic and hopefully it'll help you if you are trying to do something similar. You can find the links to these repositories in the description of this video. So first step, we want to load in the various packages that we need. And then I want to read in the boosted regression tree model. This I describe in another video. It's where I fit a model to in situ data and make predictions. So, and I've saved that as a bundle. And importantly, one of the things that's included in that bundle is a prediction function. So it's bundled in there. When I load that up, I'm going to have this predict all depths for day function that I created. And that function takes remote sensing reflectance as predictors and then makes a prediction of chlorophyll at depth. So let's go ahead, just load that in. So now I have my model. I've got the bundle. It has things like it doesn't tell you what it has. It has a model, and then it has this predict function. That's the key thing that I want. Okay, so the first thing that, let's skip that. Let's go down here. So here's the way the logic works. These are the various steps. First, I have to get my predictors, which are remote sensing reflectance from PACE. I then use those to make a prediction using this boosted regression tree model that I just loaded up. And I take those predictions and I assemble them into an X-array data set. And then I add on some derived metrics such as depth of the peak, and then I save that to a Netcdf. So I have daily files, global files of my chlorophyll at depth. So let's walk through the logic. First step, I need to get that remote sensing reflectance. So that's pretty easy using the Earth Access Python package. So I give a day, authenticate, and then I search. I'm looking for the level 3 remote sensing reflectance, and then I'm looking for a particular day, and I am going to be using the daily 4 kilometer data because that's what I trained my model on. And then I can open the results, and I can create a X-ray data set from the first file. And I guess I can run that here. Let me go ahead and run that. It doesn't take that long. Okay. So now I have that, and then I can show you what this data set looks like. Okay. So you can see it's a data set with lat and long. It's got 172 wavelengths, and it has RRS as the variable. So that's what I'm going to be using to predict. So the next step, step 2, is I create predictions. I'm going to do this for a small region so it goes fast. In my final pipeline, I'm doing this globally, but each file takes maybe a half hour to process. This will go much quicker. So basic idea is I'm going to take that data set right here that I just showed you. I'm going to get the RRS variable. I'm going to slice it to a small lat long region. Here it is, slicing it. So now I have something that's a lot smaller. It's going to be faster to work with. As I said, within my model bundle that I loaded, I put in there a predict function. I set it up that way. And so I can call predict, and what I give it is this data set with my predictors, and then it's going to put those in the right format for my BRT model. It also wants my models, and that's in my bundle in the model. It wants some other things like feature columns, but that's in the meta for the bundle. A bundle has everything it needs to create predictions. And then I want it on linear scale, so let's go ahead and run that. Okay, I just have a little progress going here. This is just showing as it's working. This is a pretty big file, and so I work through it by latitude bands. So this small area took just 8 seconds. And what does it give me? It gives me a X-ray data array, and this is for my predictions. It's at 20 depths, and you can see it's just a small little area. So this is my data array. These are my predictions. All right. And then next step is I want to put that into a data set and also add on a few other variables. And I've created this function that does that. And let's go look at what that function's like. Okay, so it's a little long, but the logic is pretty straightforward. So I take this X-ray data array, which is what I called it with, and then I say to data set. So that makes it just look kind of nice and pretty. This example of a data set where you have your variables down here. So it looks like that after I call that. Okay, so there I say to data set. So this is X-ray data array, and I'm saying, hey, change it to an X-ray data set. I add on some extra coordinates. I create this variable called the center of the depth bands. I do some validation work. Now I create my different metrics. This one is integrated chlorophyll throughout the whole water column. This one's wherever the peak chlorophyll occurs. This is where that peak occurs. This is the height of the peak. This is where the peak occurs. Depth weighted. So I add on a variety of things. I also, while I'm at it, I add attributes. Even though this takes a little time to set up the attributes, it will help me in the long run, because then when I save my Netcdfs, I already have all this information there, and anyone can see exactly what the variables are. Especially, something like this, like somebody wouldn't know what it is, so it's quite important to add a description of what that is. Same for like peak. Okay, so I set all my attributes, and then I return this X-ray data set. All right, so let's go down here. So here's where I did that, and I'm creating that data set, and this is what comes out of that. It's for my little, small region here. So now I have 20 depths, and you can see I have all these variables. You can see that this one is a 3-dimensional. It has depth, lat, and long, and these other ones are just lat, long. And then next step is I'm going to take that data set, which I just created, and I'm going to save it to a local Netcdf. So I create a temp file using this. Actually, I should also make sure that works. Okay, and then I will save that to a local Netcdf. Now, you wouldn't have to do this. My eventual goal is getting this into a cloud bucket, but I found that going cloud to cloud, so basically going from here and just trying to go from what's in memory and going straight up to a Google Cloud bucket, I found that really slow. I don't know why, but I just couldn't get it to work. And fortunately, my files are they're less than a gigabyte each, and I'm on a machine that I can deal with that. So it was easier for me to save one day at a time to a local temp directory and then upload that file into my Google bucket. So that's what I did. So here I'm saving that locally into a temp file. And then the next step is to upload that file into my cloud bucket. So here's showing how I would upload one bucket. And where exactly how this looks for your cloud provider will be different. Yeah, I'm showing it for Google Cloud, but the ideas are going to be the same. Basically, you need to do some specification that's specific for your cloud provider of how you specify a bucket. This is how you do it for Google. And then I'm going to be using, so I'm using the Google Cloud Storage package to do the uploading. So I have that installed, and here I just have to specify some details about my bucket, and then I can do uploading. So here I upload from a file name. So what I'm doing is I'm uploading that local file. And then at the end of it, I want to get rid of that local file. This is really important because I'm saving these files to the /temp directory. And if I forget to get rid of those, that directory will fill up and I'll crash my server quite quickly. So you don't want to forget to do that. Okay, so that's the basic logic. And then for the full pipeline, I'm just going to go, through one file after another, doing that same thing and just putting each file up into the Google bucket. Okay, so now, here I can test the bucket. So, here what I'm doing is I'm specifying this is GCS, Google Cloud Bucket. It's a public bucket, so I can say token is anonymous. This is the pattern of the files. I'm just finding one of the files on there. If I knew the name, I could have just put that there, but in this case, I read the file names and grab the first one. And then I can open up, here I'm going to open up 5 files together. Let's just run that and see what that looks like. So you can see there's 560 of these files. It's about, I think, 1.6 terabytes, something like that. It's just going to take a moment. So what has it done? It's lazily loaded this information. I don't have the data yet. It's just all the information about it, so I can start interacting with it and working with it. It's global here, and it has 5 time steps, and it has all 20 depths. So I can see at least the first 5 files. So my eventual goal is to create a ZAR store from these Netcdfs. Why a ZAR store? Well, it was 11 seconds just to load up 5 days, and I have 560. So if I need to do anything where I need to work with the entire data set, the very first thing I would have to do is run this for all the paths, because I've got to read in all that metadata and set things up so I can start to work with it, even if I'm going to be subsetting to a small amount. And that will take a long time. I mean, it was 11 seconds for 5 files. It's going to be pretty slow if I do the whole thing. So I don't want to be calling that all the time. And a ZAR store is a cloud native format that allows really rapid reading of large data sets. In this case, it's about 2 terabytes. That's pretty big. I can load a ZAR store immediately, and it points to where the bytes are, so I can start working with that data set without ever having to load in the whole data set. And this is nice also if I need to be doing any processes that I need to be doing in parallel. So to be doing chunk by chunk, which is what you have to do when you're working with massive data sets. You can't possibly load them into memory. So my goal is to create one of these ZAR stores from these Netcdfs. And so here's one logic that you could use. So what you can do, if your data set's pretty small, you can do this. You can, so here's my paths, which is pointing to all those Netcdfs in the Google bucket. I can do this. I can do X-ray open MF dataset. And this is setting up all that metadata. It'll understand the whole data set if I do that. It will take a long time. I don't know how long it would take, maybe 10 minutes. But I could do that. And then after I do that, I could then do this. I could specify my credentials because I have to give it's my credentials to write to the bucket, the path to the bucket, and then this. DS, the DS is this data set here, and I say to ZAR and say that mode. And what will happen in the background is because this data set is DAS backed, which means it's chunked, and to ZAR is going to use DAS, and it will do that uploading to the Google bucket in parallel. So I won't be trying to load a 2 terabyte data set into memory, which would be impossible. It's going to like chug along and chunk by chunk create this ZAR store for me. And this is a beautifully simple pipeline if your data set is pretty small. And I've used this pipeline before. It works beautifully. As you can see, it's a really short code. So definitely do that if your data set is pretty small. Okay, but my data set's not small. And I can't do that. Like, I could try, but, it would take weeks. And if anything, if my server got interrupted at any point, my ZAR store would be corrupted and I would be forced to start from scratch. So as you can imagine, that just is not going to work. That won't work. So what I need to do instead is I need to be writing this ZAR store in parallel. And I'm going to do a separate video on that. It is quite a bit more complicated, but if you're working with a really big data set, it's the way you have to go. And what that allows you to do is that now you can write your ZAR store in parallel. So for me, I can spin up 20 different virtual machines, and each of them will work one day at a time, writing to my ZAR store. And so I can, rather than something taking weeks, it is done in 5 hours. And if any file, for whatever reason, errors out, it's fine. The other ones keep working away. And then I'll just have to fix the ones that were in error. All right, the next video we'll talk about this, doing this in parallel and show you how to do that.